The next presenter is online, I believe, if the video is ready. Is that right? Yeah. So, yeah.
Hi, I'm Aaron Gember-Jacobson
hold it
from
for a
Colgate
second.
University.
Just hold it for 1 second.
Today,
sorry. I wanted to introduce you. I just wasn't sure if the video is ready. Right. OK, so the speaker is Aaron Gember-Jacobson, which we know very well, an assistant professor in Colgate University, an undergraduate-only liberal arts institution in upstate New York. His research focuses on configuration, verification, and repair. And Aaron teaches very great courses and always has a good presence. So yeah, thanks very much. Let's go ahead.
Hello everyone, I'm Nai Qianzheng. I just received my bachelor degree and work for a PhD in Peking University. Today, I'm glad to share our work, MESA, Scalable Network Testing for Programmable Data Planes.
That's the wrong video.
This is a joint work with SIGCOMM'22.
Sorry.
Hello everyone.
One more.
Hi, I'm Aaron Gember-Jacobson from Colgate University. Today, I'm going to be talking about space exploration, but not about using telescopes to explore distant galaxies. I'm talking about using network verifiers to explore a network's behavior across a large space of packet headers and failure scenarios. For example, suppose network engineers want to know which hosts can be reached from a particular point in the network. To answer such questions, we need to determine how packets are forwarded through the network. Typically, this depends on a packet's destination IP address and the forwarding rules computed by the network's control plane. For example, if we assume the network uses shortest path routing, then a packet destined for 2.0.0.2 is forwarded through routers A and B, while a packet destined for 3.0.0.3 is forwarded through routers A, B, and C. The range of possible packet headers is called the header space. And to answer the network engineer's question, we need to analyze the network's behavior for the entire header space. Now let's consider a different question. Is 3.0.0.3 reachable 99.9% of the time? To answer this question, we need to explore how our network's behavior changes when failures occur. Before, we determined that the packet destined for our host 3.0.0.3 would traverse routers A, B, and C. However, let's assume there's a 1% chance that the link between routers B and C fails. If this link fails, the traffic will now traverse routers A, D, and C instead, but our host will still be reachable. But what if there's a 1% chance that the link between routers D and C will fail? Well, if the link between routers D and C also fails, then our host becomes unreachable. The range of all possible failure scenarios in a network is called the failure space. To answer the network engineer's question, we need to analyze the network's behavior for the entire failure space. Furthermore, we need to reason about probabilistic link failures. If the network engineers instead ask, what is the maximum number of failures that can occur and still be able to reach this host, then we'd need to explore the link failures only up to the point where the first host becomes unreachable, which we refer to as deterministic failures. In summary, identifying which host could be reached from a particular point in the network required analyzing the network's behavior across the entire header space for a single failure scenario. In contrast, to understand the network's tolerance to failures, we need to analyze the network's behavior for a single header across the entire failure space. And depending on the questions being asked, we need to consider either probabilistic or deterministic failures. However, some common network management tasks require analyzing a network's behavior for the entire header space and the entire failure space, which we call the product space. And they need to consider either probabilistic or deterministic failures. For example, network engineers may be making a change to a packet filter to restrict access to the prefix 6/9, and they want to make sure that this has the intended effect, but also doesn't impact other traffic. Verifying this change has the desired effect only requires us to analyze the targeted prefix 6/9. But checking for unintended side effects is challenging because this change may impact seemingly unrelated header spaces. For example, this change that we've made also blocks traffic from the router's loopback interfaces, which prevents the routers from establishing IBGP sessions, and thus all external prefixes become unreachable. In order to verify a change like this is free from side effects, we need to verify all of a network's requirements, and these requirements typically span a large range of headers and failures. Mining network requirements is another task which requires analyzing a network's behavior across the product space of headers and failures. Many configuration verifiers require network engineers to specify a network's requirements, but these are rarely explicitly documented. So researchers have developed specification miners like config-to-spec, which automatically infer a network's requirements from its configurations. Internally, these tools invoke network verifiers to explore the full space of headers and failures, and depending on which verifiers are invoked, the requirements can either be computed for a bounded number of failures or probabilistic failures. Now, at this point, you may be thinking, Aaron, there are already so many network verifiers. Can we just use what we already have? The short answer is yes. Some verifiers are very efficient at exploring the header space because they divide the header space into packet equivalence classes, or PECs. All packets whose headers fall within the same equivalence class will traverse the same forwarding path. For example, let's consider a segment of a network with 3 routers, one of which is configured with a route filter for the prefix 192/2. And we'll assume router C receives and propagates route advertisements for the prefixes 192/2 and 128/1, which overlaps with the former. Assuming the network uses standard shortest path routing, we'll end up with the following forwarding rules. And based on these forwarding rules, all packets arriving at A that are destined for any address within the 192/2 prefix will take the same path through the network. However, packets destined for addresses within the prefix 128/2 will follow a different forwarding path. Thus, the network has 2 packet equivalence classes for traffic arriving at router A, and analyzing one packet from each equivalence class is sufficient to characterize the network's behavior from router A to any destination within the 128/1 prefix. However, if the link between routers A and C fails, then A's forwarding entry for 128/1 is updated to forward packets through B. Now there's just a single forwarding path for all packets destined for the 128/1 prefix. This demonstrates that packet equivalence classes aren't the same across all failure scenarios. So if we use verifiers which divide the header space into packet equivalence classes, we must iterate over every failure scenario of interest in order to explore the product space, and this is inefficient. To efficiently explore the failure space, we need to turn to verifiers that divide the failure space into failure equivalence classes, or FECs, such that failure scenarios belong to the same FEC, result in the same forwarding behavior for a specific prefix. Here again is our example network, but we're only considering the advertisement for the prefix 192/2. We saw before that in the absence of failures, router A forwards traffic for this prefix to B and then along to router C. The same is true if the link between routers A and C fails, because we weren't propagating the route advertisement over this link anyway. However, if the link between routers A and B fails, then there's no path from router A to the 192/2 prefix. Similarly, if the link between routers B and C fails, again, there's no path from router A to the 192/2 prefix. In fact, any combination of failures that involves either the link between routers A and B or the link between routers B and C will result in the same behavior, no forwarding path. Thus, for the prefix 192/2, there are 2 failure equivalence classes. However, for the prefix 128/2, the failure equivalence classes are different. Hence, if we use verifiers which divide the failure space into failure equivalence classes, we have to iterate over every packet header of interest in order to explore the entire product space, and this is inefficient. Likewise, there are some verifiers that are optimized for deterministic failures, while others are optimized for probabilistic failures, but I won't go into these details. To explore the product space of headers and failures in a scalable and general way, we introduce a new verification engine called SRE. SRE is designed to efficiently scale network analysis to the product space of headers and failures by computing packet failure equivalence classes, or PFECs. Additionally, SRE generalizes to both deterministic and probabilistic failures by delaying the binding to a failure model. The fundamental approach that makes SRE scale is symbolic execution, which is a way to abstractly execute a program by making the input symbolic. In this example, we'll use a question mark to represent an arbitrary integer value entered by the user. As we proceed with the execution of this program, we encounter a branch condition and observe there are 2 possible ways the program can proceed. With symbolic execution, we follow both paths and track conditions the symbolic input must satisfy for each execution path to occur. By doing this for the entire program, we can identify all possible execution paths, and we can identify equivalence classes of inputs that result in a particular path being taken. We employ a similar principle to compute packet failure equivalence classes. In particular, we can view a network's control plane and data plane as two separate programs, which we can create a model for. The control plane takes router configurations and the available links as input, but in SRE, we make the state of each link symbolic and symbolically execute a model of the control plane. This results in symbolic routing tables, where each entry contains a set of link conditions that must be true for the entry to exist. The symbolic ribs are then provided as input to the data plane model, along with packets whose headers are also symbolic. We then symbolically execute this model of the data plane to obtain a set of packet failure equivalence classes, which are encoded using a binary decision diagram, or BDD. I won't go into the details of how we conduct symbolic routing and packet forwarding due to the limited amount of time, but I do want to show you how the BDDs encoding the packet failure equivalence classes can be used to efficiently answer questions like those I mentioned at the beginning of the talk. Here, a network engineer is interested in knowing how many failures can occur and still have traffic that arrives at router A be able to reach any host within the 128/2 prefix. First, we identify the path through our BDD that is associated with this particular packet header, namely where the first bit is a 1 and the second bit is a 0. We then look at the subset of the BDD that corresponds to this particular header space. And in order to compute the network's failure tolerance, we compute the length of the shortest path to the terminal node 0, indicating that there is no forwarding path. By computing the shortest path, which in this case is 1, when we weight the dashed edges as 1 and the solid edges as 0, gives us a failure tolerance level of 2 - 1, or being able to tolerate a single failure. Now, if the network engineer instead wanted to know what is the probability that A can reach 128/2, we simply assign weights instead of 1s and 0s to the edges, where we weight a link as being either available with a 99% probability or unavailable with a 1% probability, or whatever's appropriate for the network being studied. We can compute the probability of A being reachable by computing a weighted sum of all paths to the terminal 1 node, which means there exists a forwarding path. Let me briefly show you how efficient SRE is for simulating and computing all pairs reachability for some real networks. Here, we study 5 networks, 3 WAN topologies, and 2 fat tree topologies, which are typical of data center networks. For each of these, we limit the number of maximum possible link failures that SRE will consider before stopping to follow particular execution paths, and this just helps avoid state space explosion. We compare SRE's performance against 3 state-of-the-art verifiers: Batfish, which is optimized for packet equivalence classes, Minesweeper, which is optimized for failure equivalence classes, and Tiramisu, which is somewhere in the middle. Here, we observe that for the WAN topologies, SRE is always about 10 times faster than the fastest existing verifier, Tiramisu, regardless of the maximum number of failures that we consider. For fat tree topologies, SRE's performance is more comparable to that of Tiramisu, especially as we consider a larger number of failures, because there's more symbolic paths that SRE needs to consider. But even in this case, SRE's performance is still comparable, and so we still get scalability and generality without significantly compromising on performance relative to more specific optimized verifiers. So in summary, I've talked about symbolic router execution as a way to scale network analysis to the product space of headers and failures by computing packet failure equivalence classes. And I've talked about the fact that this generalizes to both deterministic and probabilistic failures by delaying binding to a failure model until we've computed the prefix. With that, I'm happy to take any questions.
Thank you very much. Question time. Floor is open. Please ask for a microphone. And yeah, there's one back at the very back behind.
Thank you. Thanks for great presentation. Ashkan from Huawei, Canada Research Center. I'm just curious about actually why you use actually BDD actually for doing the formal verification instead of some approach like the SAT solving. Yeah, thanks.
Yeah. So it turns out that other approaches like Huiyan do use SAT solving as a way to encode these conditions, but these reach time limits in terms of computing the conditions for a path and conjuncting additional conditions. So BDDs are actually a more efficient way to represent this and do disjunctions and conjunctions. And then also it allows for the really efficient analysis of the actual policies that we want to check, as I showed toward the end of the talk.
Cool, thanks. Any other questions? There's one here. Just raise your hand a little bit stronger so you're visible.
Hello, Alexander Markovic from Vrije Universiteit Amsterdam and volunteer at SIGCOMM'. Thank you for the talk. I was wondering at the benchmarking graph for K3, the value was better than for K2. How does that come? Do you have an explanation for that?
Yeah, so it has to do with the fact that there are certain prefixes that are only reachable for a maximum number of failures. And so they end up getting pruned out when we consider differing number of failures simply because of the amount of redundant paths. And so you end up with this anomaly for K2. And it'll differ based on the topology and based on the number of available paths for certain prefixes in the network.
All right, thank you.
So much. One more.
Hi, great talk, Aaron. This is Brighton Godfrey from UIUC and VMware. Can you give some intuition for, as you're computing the failure equivalence classes symbolically, when does the algorithm successfully kind of coalesce different possible execution paths? And when does it have problems where it maybe, did you encounter problems where it kind of doesn't find equivalence classes, even though the ultimate outcome, the answer that you're going to give, ends up being the same?
Yeah, so that's a great question. So there are instances where you can end up with many packet failure equivalence classes if you were to look at sort of consistency across all failures or consistency across all packet headers. So basically, if you try to do this in the PEC or the FEC way, you end up with a lot of different cases. But the packet failure equivalence classes sort of naturally capture this case where you might say for this prefix and this failure, this path gets used. For a different prefix and a different failure, this same path gets used. And the PFECs really are able to condense those things together in a way that you just can't do if you only look at packet or you only look at failure. So you sort of naturally get this recognition of the fact that it really is different on a prefix and a failure basis, but the PFECs really can combine these things together.
Cool, thanks very much. Any other questions? We are good to go. Thank you very much, Aaron. Thank you. Thanks. Great.